Okay, picture this. It's early morning at Kennedy Space Center in Florida, the sky still carrying that soft pre-dawn glow, when suddenly the calm is shattered by the roar of engines and a pillar of fire streaks into the heavens. That's not just any rocket launch. That's SpaceX's Falcon 9 taking 3 different spacecraft on a journey that pushes human curiosity far beyond our daily lives here on Earth. These aren't ordinary satellites designed to beam down television or guide your GPS. These are probes with a mission that could literally change how we understand our relationship with the sun, the invisible storms swirling through space, and the very edge of our solar system. If you've ever wondered how scientists monitor the hidden forces of space weather, or what stands between us and the galaxy beyond, this mission is exactly the kind of story you'll want to lean in and follow closely. So let's break it down. On board this Falcon 9 were 3 very different but closely connected probes. NASA's Interstellar Mapping and Acceleration Probe, which you'll hear a lot about under its shorter name, IMAP, along with the Carruthers Geocorona Observatory, and NOAA's Space Weather Follow-on spacecraft, often called SWFO-L1. Each of these machines is headed to the same destination, a special point in space called the Sun-Earth Lagrange Point 1. Think of it as a cosmic balance beam, located about 930,000 miles away from Earth, where the gravitational tug of our planet and the sun cancel out just enough to make it an ideal observation spot. From there, these spacecraft can stare directly at solar winds, particles, and radiation without Earth constantly getting in the way. And let's not forget the teamwork involved. This mission represents collaboration across multiple agencies and scientific communities. NASA brings IMAP, NOAA brings SWFO-L1, and CGO builds on decades of heritage in atmospheric science. SpaceX provides the launch capability, but hundreds of scientists, engineers, and project managers across institutions had to coordinate schedules, designs, and instruments to make this launch possible. It's the modern version of what exploration has always been. Not one person venturing alone into the unknown, but a network of minds pooling expertise for a common goal. That's part of what makes following space exploration so rewarding. It's humanity working together on challenges bigger than any one nation or organization. The star of the mission is IMAP, NASA's $600 million effort to answer some of the most profound questions about our solar environment. Imagine a bubble that surrounds our solar system, shaped and controlled by the sun's magnetic field and its constant stream of charged particles called the solar wind. This bubble is known as the heliosphere, and it's like a protective shield against galactic radiation. But here's the catch. We don't fully know where this bubble ends or how exactly it interacts with interstellar space. IMAP carries 10 cutting-edge instruments designed to measure solar wind, capture data on interstellar dust, and detect high-energy particles. In other words, IMAP is our scientific scout, mapping the outer frontier of our solar neighborhood. Now let's add some perspective here. Why should anyone care about the heliosphere or the boundary of our solar system? Well, think about the fact that every astronaut we send beyond Earth's protective magnetic field, like those who will eventually travel to Mars, will face exposure to harmful cosmic radiation. Understanding how solar storms and interstellar particles move through space can provide critical data that leads to better shielding, safer mission planning, and accurate radiation warnings. IMAP isn't just about science for the textbooks. It's about the future of human exploration. The spacecraft will also provide near real-time updates to help NASA keep missions like Artemis, which aims to return humans to the moon and eventually extend further out, as safe as possible. Alongside IMAP, the Carruthers Geocorona Observatory, or CGO, carries its own important role. This probe will study the very outer edges of Earth's atmosphere, called the exosphere. To give you a visual, the exosphere is so thin that it doesn't even feel like an atmosphere, but it's still where atoms of hydrogen scatter sunlight and create a faint ultraviolet glow. NASA refers to this as the geocorona, and it's something astronauts on Apollo 16 first measured decades ago. CGO's mission is to take that legacy further, capturing images of this ultraviolet glow and helping us understand how solar activity can strip away particles from Earth's outermost atmospheric layers. If you care about climate science, satellites, or even the long-term habitability of Earth, this data becomes crucial. Then we've got NOAA's SWFOL-1 spacecraft, and this one is all about early warnings. Solar storms, those massive eruptions from the sun that hurl energy and particles across space, can have real consequences here on Earth. We're talking about power grid failures, satellite malfunctions, radio blackouts, and risks to astronauts living in orbit. The Space Weather Follow-on satellite is like an advanced weather forecaster, parked perfectly at L1 so it can spot dangerous solar activity before it hits Earth. Think of it as a cosmic early alert system that could help power companies, airlines, and even space agencies take protective measures before the worst effects arrive. In an increasingly tech-dependent world, these warnings aren't just handy, they're essential. Now let's talk about the ride that made all this possible. SpaceX's Falcon 9 rocket lifted off at 7:30 a.m. Eastern Time, carrying all three spacecraft stacked together in its payload fairing. About 9 minutes later, the rocket's first stage booster nailed its landing on the drone ship, just read the instructions, stationed out in the Atlantic Ocean. For SpaceX, this was nothing new. It was already the 120th Falcon 9 flight of the year, and the second use of this particular booster. But if you zoom out, that level of reliability is what allows NASA, NOAA, and other partners to confidently plan ambitious missions like IMAP without worrying about the costs skyrocketing. Reusability is reshaping how often and how affordably humanity can reach space. The deployment sequence of the satellites was carefully choreographed. First, IMAP separated from the upper stage roughly 84 minutes after launch, beginning its journey toward the L1 point. Just a few minutes later, SWFOL-1 followed suit, and then the Carruthers Geocorona Observatory rounded out the trio. Each spacecraft will now spend weeks making small adjustments, using onboard propulsion to fine-tune their orbits until they settle into position nearly 1 million miles away. Once they're up and running, they'll beam back a steady stream of data that scientists across the globe will analyze. It's the kind of international, cooperative science that fuels not just discoveries, but also practical benefits for everyday life. It's worth noting that space weather research isn't just an abstract curiosity. In 1989, a massive solar storm actually knocked out power across the Canadian province of Quebec for 9 hours. That was more than 3 decades ago, when our dependence on satellites and electronics was nothing compared to today. Imagine the impact now, with GPS guiding everything from airplanes to financial transactions, with Starlink and other networks connecting rural communities, and with astronauts preparing for deeper space exploration. That's why missions like these aren't optional extras. They're fundamental to protecting the infrastructure of modern civilization. But there's another angle to this mission that sparks pure wonder. By mapping the heliosphere and better defining its boundary, IMAP is essentially sketching the edges of our cosmic neighborhood. It's like looking at a globe and finally being able to outline where the oceans end and where new continents begin. For decades, we've known that the Voyager probes, launched back in the late 1970s, eventually crossed into interstellar space. But they're aging, and their instruments are limited compared to what modern science can do. IMAP builds on that legacy, giving us a sharper, clearer picture of how our solar system interacts with the rest of the galaxy. It's human curiosity at its finest, asking what's out there and actually building the tools to find out. So as we look at this mission as a whole, what's the big takeaway? 3 spacecraft, 3 unique objectives, but one shared purpose. Understanding how the sun shapes our lives and how the vast boundary of our solar system connects us to the galaxy beyond. Whether it's providing radiation warnings for astronauts, protecting power grids from solar storms, or mapping the edge of the heliosphere, these probes are investments in both knowledge and safety. And with Falcon 9's flawless performance adding yet another chapter to the growing story of reusable rockets, it's clear we're living in a golden era of space science. The question now isn't whether we'll learn something groundbreaking, it's how soon. And that, my friends, is the kind of mission update that deserves all the attention it's getting.